Digital filters typically have one input and one output. A signal is applied to the input and a modified signal is produced at the output. A digital signal is basically a stream of numbers, usually spaced evenly in time. The signal is usually modified in some frequency-dependent way so that wanted frequencies are retained and unwanted frequencies are removed. MicroModeler DSP is a digital filter editor. You choose from a variety of digital filters from the menu bar and drag one to your application. You then use the handles and controls to interactively adjust the filter's response while viewing the various graphs and curves. Code, coefficients, and test cases are automatically generated, which you then copy and paste into your project. In your application, you create an instance of the filter, write a stream of numbers into its input, and read a stream of numbers from its output. We'll open MicroModeler DSP and select a digital filter from the toolbar at the top and drag it to our application. We'll choose a moving average filter because it's one of the simplest types of filters. After you drop the filter, the displays will be updated automatically. A moving average filter simply stores a history of the last n samples and outputs their average. At the top right, we see the graph of magnitude versus frequency, or how much different frequencies will be amplified or reduced by the filter. We can see that averaging filters a signal, retaining the low frequencies and reducing the high frequencies. We can control the number of previous samples that it averages by adjusting the filter length n. By adjusting this, we can see that we have some basic control over which frequencies can pass and which are discarded. If we look at the structure view, we can see what the inside of a moving average filter might look like. The z to the -1 symbols mean delay by one time step, and the plus symbols mean add or combine the signals. The white arrows mean multiply the signal by the amount shown to the right of the arrow. The chain of delays is called a delay line, with the input signal being delayed by one additional time step as you proceed. For an average of 5 samples, we take 1/5 of the most recent sample, 1/5 of the second most recent sample, and so on. The white arrows are also called taps, so you could almost imagine them as being taps like the one in your kitchen sink that are all 1/5 open. You can imagine the signal flowing in from the left and being progressively delayed as it moves along the delay line, then being recombined in different strengths through the taps to form the output. If you can understand this, then you can get an idea what an FIR filter is. An FIR filter is identical to the moving average filter, but instead of all the tap strengths being the same, they can be different. The next section will introduce you to finite impulse response, or FIR filters. By varying the tap strengths, we can create close to any frequency response that we want. In this tutorial, we'll look at finite impulse response filters. We'll open MicroModeler DSP and click on the Designed Filters menu. We'll choose an equiripple filter designer from the toolbar at the top and drag it to the application. After you drop the filter, the displays will be automatically updated. With this filter, we can design almost any frequency response that we want. Using the magnitude frequency graph at the top right, we can use the control points to edit the shape of the response. We can move control points around. We can drag new control points from the menu bar to the graph. The del key deletes the selected control point, and we can also use the right-click menu to insert or delete control points. We can also adjust the length of the filter. A longer filter uses more CPU on the target processor, but gives a more accurate frequency response. For more precise control, the control point coordinates can be entered manually. We can also adjust the type of curve or line used to connect the points. FIR filters are not very good at handling sharp changes in frequency response. If we reduce the width of the transition band, ripple increases, which can be counter-reduced by increasing the filter length. You will find that when designing FIR filters, you will have to trade transition rate, ripple, and filter length with each other. If you look at the graph at the bottom right, you will see the impulse response of the filter. For FIR filters, the tap strengths and impulse response are the same and are known as the filter's coefficients. Everything we need to know about how the filter will behave can be determined from its impulse response. You can also design FIR filters in the same way using the frequency sampling designer. Sometimes there can be ringing where there are sharp edges in the desired response. This is known as the Gibbs phenomenon. You can specify a window function in the dialog to reduce the Gibbs phenomenon, which smooths the edges of the impulse response. There are a variety of window functions you can use. The easiest way is to experiment with them. Some of the window functions also have a window value, which provides additional control over its shape. Instead of using control points to define the frequency response, you can also drag a specification to your filter, which will automatically manage the frequency response and control points for you. Let's try dragging a low-pass specification to our design. If you go to the frequency response view, you can adjust the passband ripple, stopband ripple, passband edge, transition bandwidth. The specification will estimate the filter length for you, although you may want to fine-tune it afterwards. Now that we can design filters, the next step is to use them. The next tutorial will cover getting code and data out of MicroModeler DSP so that we can do something practical with it. If we go to the coefficients view, we can see the coefficients used to describe the filter in numerical form, which we can copy and paste into other applications. If you're using a third-party DSP library, a third-party product, or writing your own code, then you can select, copy, and paste these directly. The first set of coefficients is in floating point format and are for a whole filter. If you're developing for an embedded system, then your device might not have a floating point unit, or you may choose integer arithmetic because it is faster. To select integer arithmetic, use the arithmetic field to select the word lengths for memory, coefficients, and accumulator. If your hardware multiplier multiplies two 16-bit integers to produce a 32-bit result, then one of the 16 by 16 options usually performs best. When using integer computation, you can enable the filter simulator by clicking on the right-hand graph buttons. The simulator will imitate the effects of integer roundoff and is a good way to spot if the real filter will work in the same way as the theoretical one. With 16-bit arithmetic, the curves are almost the same, but with 8 by 8 arithmetic, the frequency response can change due to pole zero shifting. The shifted poles can also be seen in red on the z-plane view. The remaining coefficients are presented in fixed point integer form if applicable. If multiple sections are present, the coefficients are separately listed for each section. If we go to the code view, we can see that it has automatically generated C code for the filter, which we can copy and paste into our project. The header is listed first, followed by the C file. Large projects can have many symbols and variables, and we want to ensure that our filter does not collide with the names of other functions or libraries. We also want to give our filter a meaningful name so that we can identify it. You can use the class field to change the name of the filter. All of the functions and structure definitions are prefixed by this name, ensuring their uniqueness. The frequency response of a digital filter is always measured relative to the sample rate, which is the speed in samples per second that numbers will be fed into the filter. The default is 1 Hz or 1 sample per second, but a typical audio application might use, say, 48,000 samples per second. We can enter this value in the sample rate box, and our displays will be updated to reflect the sample rate of that signal. I've set up a small test project for an ARM-based microcontroller. I've created an empty header and source file where I'll paste the filter and some simple code to use it. We'll select the header code, copy to the clipboard, and paste to the header file. We'll do the same for the source file. If we look at the main function, we create a new instance of the filter here. When we're done, we would destroy the filter here. In the main loop, we read a value from an analog to digital converter, then write it to the filter. We read the output from the filter and write it to a digital to analog converter. The user supplies the code to interface with the ADC and DAC. To test, we'll compile the project, set a breakpoint, and debug. We can also enable test cases that we can run to test our filter. These can be selected at the bottom of the code view. In the next section, we will cover infinite impulse response, or IIR, filters. We covered finite impulse response, or FIR, filters in a previous tutorial, and the other main type of filter is the infinite impulse response, or IIR, filter shown here. We can see that the right half is a typical FIR filter, rotated on its side from the previous tutorial, and the other part of it is like an FIR filter that feeds its output back to the input. Because there is feedback, very complex behavior and long impulse responses can be achieved for a short delay line. If we remove the left half, we would have an FIR filter, and the impulse response would end after 3 time steps. With the feedback part, we keep recycling the signal, producing a much longer impulse response. This is how they get the name infinite impulse response filter. Let's drag an IIR filter to our application. They are all very similar but differ in subtly different ways. The best way to understand their differences is to experiment with them. We'll start with a butterworth filter. IIR filters usually get their names from the mathematical functions that define their frequency response. As you move the cursor, you can see that there is a handle that lets you change the cutoff frequency of the filter. You can also set this value in the Properties dialog to the right. As with FIR filters, you can also adjust the length of the filter, which gives a sharper response at the expense of more computer time, via the order field. By changing the type of the filter, you can select the pattern of frequencies to pass or remove. Low pass allows low frequencies to pass, but excludes high frequencies. High pass allows high frequencies to pass, but excludes low frequencies. Band pass allows only a selected band of frequencies to pass. Band stop removes a selected band of frequencies. More complex filters can be made by combining multiple filters in series, chaining outputs to inputs, or parallel by summing outputs. Let's look at a different IIR filter. Let's drag an IIR elliptic filter to our application. This is the most complex IIR filter, but it will help us understand the other ones. Most of the other IIR filters can be made from the elliptic filter. This time there are handles to control the passband ripple, stopband ripple, the width of the transition band, and the cutoff frequency. As with FIR filters, you will have to trade filter length or order, transition band width, and ripple with each other depending on your requirements. Let's experiment with the other IIR filters. The Butterworth has a flat passband and stopband, and a wide transition band. Chebyshev Type 1 has controllable passband ripple and a flat stopband. Inverse Chebyshev Type 2 has controllable stopband ripple and a flat passband. The elliptic has adjustable passband ripple, stopband ripple, and transition band width. With a Bessel, only the cutoff frequency can be adjusted. Bessel filters have a group delay that is reasonably constant across the passband, reducing phase distortion, which we will cover later. While IIR filters are extremely fast and can provide very sharp changes in frequency response compared to FIR filters, they have at least one major drawback: phase distortion. Phase distortion occurs because signals of different frequencies are delayed differently when crossing the filter. If you click on the graph's group delay icon, you will see a graph of how much a signal of a specific frequency is delayed. If you do the same thing for an FIR filter, you see a straight horizontal line, meaning that all signals are delayed by equal amounts, which is good. For elliptic filters, phase distortion is especially noticeable at the edge of the passband. If we look at the structure view, you will notice that instead of having one long filter, it has been split into smaller subfilters or sections called biquads. Having a large amount of feedback in the same filter can cause the filter to be unstable. Splitting it into biquads solves this problem. In the next tutorial, we will cover topics such as transfer functions, poles, and zeros. Let's drag a Butterworth IIR filter to our project. On the Z-plane and transfer function views, you can drag the mouse to rotate or pan the view. Rolling the mouse wheel will zoom in and out. The transfer function view is basically a 3D view of the Z-plane view. If you rotate it so that it's flat, you can see that we are actually looking at the same thing. On the Z-plane view, the X's are called poles and the O's are called zeros. If you rotate and examine the transfer function view, you will see that it gets pulled up by the poles and pulled down by the zeros. It is the positioning of the poles and zeros that controls the shape of the transfer function, which then defines the shape of the filter's frequency response curve. The outside of the circle is called the unit circle because it has a magnitude of 1. The unit circle is where the Z-plane meets the frequency domain. If we enable decibels or logarithmic scaling on the graph view and rotate, we can see the frequency response at the intersection of the transfer function and the unit circle. We should now begin to see how these three views are related. We'll drag a blank filter to the application, then add a pair of conjugate poles. The conjugate poles are paired and mirrored across the horizontal axis of the Z-plane. We'll grab the pole and move it around. In the frequency response, you'll see that a peak follows the pole as you move it. Moving the pole towards the unit circle will cause the peak to become stronger. Moving it towards the center will cause it to become weaker. Rotating the pole around the center towards the left will cause the peak to increase in frequency. Variable z is a complex number, which means that it has two coordinates that can be expressed as a radius and an angle. The radius corresponds to magnitude, and the angle corresponds to frequency. If you look at the impulse response, you will see that the filter will ring at the frequency corresponding to the pole. When the pole is inside the unit circle, the impulse response will decay exponentially. On the unit circle, it will oscillate forever at that frequency. If the pole is outside the unit circle, the response will increase exponentially, which is unstable. Filters never have poles outside the unit circle because this produces an unstable filter. We'll add a Butterworth filter. If you go to the structure view, you will see two rows of equations at the top. These are the filter's transfer functions. The transfer function view is a graphical representation of this function. The top one is in pole zero form, and the bottom one is in polynomial form. They are both the same equation, and the bottom one can be obtained from the top one by multiplying its terms together. The pole 0 form has the negative coordinates of the zeros on the top row and the negative coordinates of the poles on the bottom row. When the top row equals 0, the transfer function will be 0, and this corresponds to a 0. When the bottom row equals 0, the transfer function will be infinite because we are dividing by 0, and this corresponds to a pole. We can see that when z equals -1, -1 plus 1 equals 0, the top row will be multiplied by 0, the transfer function will be 0, so we say that there is a 0 at z equals -1. When z equals 0.548 plus j 0.234, the bottom row will become 0. We are dividing by 0, so the transfer function will be infinite, and we say that there is a pole. When we multiply out the pole 0 form of the transfer function, we get the polynomial form. The polynomial form gives you the coefficients of the filter. The top row gives you the feed-forward coefficients, think FIR, and the bottom row gives you the feedback coefficients, think IIR. The transfer function of an IIR filter has both a numerator and a denominator, but the transfer function of an FIR filter has only a numerator. This is the last in the series of our introductory DSP tutorials. We hope to shortly cover a new series of tutorials covering more advanced topics in DSP and digital filter design.